Okay, now we have to solve example 3.4, a sliding and spinning dumbbell. So here you can see this is a dumbbell which consists of some mass which is mounted on the end of a rigid massless rod of length 2p. When we apply some external force which is called impulse on the left side of the dumbbell, it always moves along the direction of y. You can see. Okay, now you have to find the subsequent motion which is along these direction. So we have to consider first external force. Both quantities are vector because we have to deal with direction. Okay, so this is the first order derivative of momentum and this is the external force. The total momentum after the impulse is this. So what is the impulse? Impulse is just a force which is acting for a very short time interval on some object. Okay, so you can see we have the simplest formula for momentum, which is mass into velocity. Okay, further you can see after arranging the term, velocity can be written in this form, which is the first order derivative as symbolic representation of dot. Okay, so these velocity is actually for the center of mass. Okay, after arranging this capital M is the total mass, and after putting the value of this capital M, which is 2m, you can see there are two mass. Okay, so further you can see, okay, this is the formula. Now you have to apply the momentum value, which is force into time interval, and 2m remains same. So force is acting, so it's always there is a torque because we deal with the some rotational object. Dumbbell is rotated clockwise, so we have to consider some external torque, which is also force, and which is the cross product of moment arm and force of action. So here the moment arm, which is the distance, which is denoted with b, multiply force. Okay, so you can see that a cross product of two vectors can be written in the form of angle. So here you can write any unit vector. It is there, z unit vector. Okay, angular momentum of the dumbbell is this. This is the formula for angular momentum. Now arrange the term again. You can write b instead of r because this is the distance we denoted with this letter. Okay, so momentum is always equals to force into time interval, which is actually a impulse. Okay, now as we have the moment of inertia, and when we talk about the moment of inertia, so you can see the moment of inertia is applied only for rotational objects. Okay, so this is the angular momentum, and this is the moment of inertia, and this is the angular velocity. After putting the values, you can see, and arranging the values and take the value of this angular velocity, you will get these equations. So r square, you can write there b square instead of r because we already write there. You can see these b square and these b, 1b is cancelled, and remaining we have only 1b, which is the distance actually. Okay, so by the same, okay, further you can see by the same, the right mass is moving down relative to the center of mass. Its total velocity is initial velocity. Okay, so you can see this is the velocity for right dumbbell, right mass. Okay, which is equals to this velocity, which is actually we find for center of mass, and here you can see there is a deduction of this angular velocity with into b. This is the distance. Okay. Okay, further you can see after putting the values which we found for this velocity and this omega value is this, which is this, and after cancelling these both we will get same terms, and the difference of this term will be 0. So what we get, the right mass is initially stationary. It's obvious because this is 0. Okay, while the left one carries all the momentum force into short time interval of the system. So this is all from my side. Thank you.